Thank you. Thank you also to the organizer for the opportunity. So what I would like to present today is essentially we are going to focus on downscaling of climate model by using some machine learning techniques. So actually we are from an institute that is working on adaptation, and climate simulation are essential for the work. Nevertheless, we need, for regional adaptation study, we need some systematic, some simulation where the systematic bias coarse resolution is resolved. So we can actually address this issue by using dynamical downscaling, usually, and that focus on physical principle, but essentially is expensive from the computational point of view. Or we can use statistical downscaling, and in this case, for example, the application really on statistical relationship that actually are learned during the historical period and then are applied also to the future. So you can see, for example, here a data set that we are currently use of downscaling of a climate model to the kilometric resolution. Is the NIS 2020 data set. So the focus today is try to apply the machine learning technique to try to overcome this limitation of the statistical downscaling. At least we try to do that. So here you can see the approach. So it is called perfect prognosis approach. So it's quite simple if you look at the sketch here. Essentially, we use large-scale predictor from reanalysis, and we try to simulate some target variable that is very high resolution. It is an interpolation dataset of observation called narrow dataset. So actually we build this machine learning based model, and we evaluate the model without of sample observation, and then we use this model to try to downscale coarse simulation to high resolution. Obviously, it is based on some assumption, and different, for example, of one assumption is that the model, the general circulation model, must simulate the predictors. And also the machine learning model should remain effective also in the future. So it is quite quickly again on the approach. We use the CNN algorithm where we essentially we include as a predictor a big set of variables at different level of altitude, and we include also dynamical and also thermodynamical variable to try to for essentially for many reasons, but because also we think that is can provide a better climate change signal in the prevision. And then you see the output at the very high resolution. What I will show you is essentially at the scale of 2 kilometers, what I will show you. So very big jump. So it is an example of the evaluation of this approach for the Kanto region. So essentially here we compare this approach with different architecture of the same algorithm, or different algorithm also, and it is for several variables. And what you can see in this evaluation is that the approach that we select, so I mean the algorithm result and the best result in terms of explain variance and absolute error essentially for all variables. So we use this for try to downscale simulation. Now, what I show you here is directly the application of the algorithm to the simulation. We took a model from the CMIP6 dataset and we downscale. And I show you the climate change signal in the original simulation and in the downscale. You can see downscaling account in such way of the influence of the mountains over here on the southern part here. And but what is also important is that it looks like that climate change signal is still preserved here because it is an issue of the machine learning. So when you try to extrapolate outside your range of observation. Now something more to say that we use a dedicated model for each variables. And so we can think about some problem related to the fact that maybe using a different model for each different variable can produce some inconsistent correlation among the different variables. So here is an example, so a case study focus on solar power. Essentially, we focus on photovoltaic potential because, okay, it's interesting from the point of view of the future solar power generation, but it is also interesting for us from the technical point of view because this photovoltaic potential or solar cell essentially are also affected by temperature and wind speed. So we include in this downscaling, we include all information, not just solar radiation, but also wind speed, temperature, and then we do the computation on downscaling. And again, you can see that the signal is preserved. So I move on with another case study. Here we try to do something a little different, the sense that we try to downscale an ensemble of model to try to reproduce snow depth. The approach is similar to what we already talked before, and we have no long time to enter the detail, but it is essentially the application of the model for the historical period, for the future, and is again the climate change signal in snow depth. And what you can see in this signal is that it is more or less coherent with what we have also on regional climate model. So this reduction of snow depth is stronger at lower altitude, and is in percentage is essentially smaller at upper altitude. It is more or less coherent with what we think. And you can see in the bottom some additional application, for example, for adaptation study. For example, here on the left side, you can see the impact on the potential impact on skiing, on ski areas. So essentially, we compute the snow cover days based on this data set, and what we see that potentially this area will have some problem. I mean, this parameter is important because based on the snow cover days, people can understand is still convenient to keep open the ski areas for from the economic point of view or not. So that's why could be interesting. And some other consideration for water supply. So the last case study is essentially focused on precipitation. As I mentioned also from the previous speaker, actually is quite difficult to evaluate, to simulate the precipitation in machine learning. So we tried to make some modification in the algorithm in the sense of not simulating the amount of precipitation, but instead simulating the parameter of the distribution of Bernoulli and gamma. So in such a way we have the output, essentially the output of this model is now the probability of precipitation and then the two parameter of the gamma distribution. So we have some kind of stochastic approach in this way. And this is the result. For example, you see that the precipitation here is the pattern in the observation, and the simulation is quite similar. The bias is quite smaller in terms of percentage. Also, the reproduction of annual wet days is coherent. And still we have some advantage in trying to reproduce the extreme events. For example, it is again the bias between the model and the observation for the most extreme precipitation events, and you can see that is better than what we can have with a different approach. So yeah, you can see also some time series here with the envelope that is coming essentially from the distribution. So here is my concluding remark. So in general, we try to downscale climate simulation with this CNN algorithm with machine learning, and we are trying to understand the advantage of doing that with respect to the usual techniques. And it's important to say that up to now we use as a reference some interpolate observation at very high resolution, so we expect to have some improvement or get some new thinking from using regional reanalysis, because that could be the next step. You can see also the poster here. So that's essentially, that's it from my side.